Thank you. And we're going to go ahead and continue with one of the student intern presentations. We have Brandon Cruz Chavez from UT Austin, and he's talking about assessing additive manufacturing for liquid-cooled hypersonic vehicle leading edges.
Okay, so at this point, I should have my presentation up. So my presentation is over additive manufacturing of liquid-cooled hypersonic vehicle leading edges. But before I get into that, let me sort of introduce myself. My name is Brandon Cruz, and I'm a third-year mechanical engineering major at UT Austin. Over the summer, I did some research over this topic, and I'm excited to talk to you today about some of the findings of that research, as well as introduce, or I guess go more into the topic of hypersonic vehicle leading edges and additive manufacturing and just manufacturing in general for defense applications in aerospace. So it's interesting that we just had somebody from Boeing talk about this. So I'm hoping he can give us some good discussion about this topic as well as we discuss this research. But I'm from University of Texas at Austin, and here we have many research facilities on campus and offsite. This summer, I was working on one of UT's offsite research campuses. It's still technically on campus, but it's disconnected from the main campus. It's about 25 minutes away. This place is called the Center for Electromechanics, and here's where they've done a lot of different military and defense testing, as well as materials processing, materials research. And so I got to work with some very, very important and innovating people in this field. One of which was Dr. Beeman, who was one of my mentors and sort of my supervisor. He's actually the person who invented the SLS additive manufacturing process, which I think is really interesting. Well, it was developed in his lab. And that's a process that they use all the time now for the polymer 3D printing that maybe they have at a library at your school or something like that. So I think it's very interesting to have been able to talk to and work with somebody like that because they definitely know what they're doing. And it's given me an awesome opportunity to learn about this field and additive manufacturing in general. So let me start to introduce the problem that my research aimed to address. So we talked a little bit about before hypersonic vehicles, what they are, maybe what they can be used for. I'll sort of review that really quick, and we'll narrow down into one very specific part of the vehicle that is of extreme interest because of the extreme loads it faces, both thermal loads and aerodynamic loads. So hypersonic vehicles are defined as by NASA as speeds of up to Mach 5. So this is typically a speed reserved for orbital reentry vehicles like Brian was talking about. But they're really trying to make this into an airplane speed. They're trying to develop more airplanes with these kinds of speeds, both for time-sensitive payload deliveries for the military, as well as commercial aircraft potentially for civilian value. And there's a lot of high temperature science that is necessary for space exploration, like Brian was saying, like going to Mars and such, that figuring these things out becomes very necessary. So there's a lot of value in different sectors here. So this is a very cutting edge area of research and one that many different groups have a lot of interest in. Now, that's hypersonic vehicles, but let's narrow down into the leading edge specifically. The leading edge is that forwardmost part of the aircraft. And in the picture, you can see it's like glowing red hot because of how hot it is. And the temperatures are for hypersonic vehicles are almost always above 1,000 degrees Celsius. In often cases, many times that, it's like 3,000 degrees Celsius is pretty common for a hypersonic vehicle. And this problem where the leading edge is glowing red hot, experiencing a lot of wear and a lot of thermally induced stresses is so characteristic of the vehicle that they're always shown glowing red hot this way. And that's actually accurate, and it's sort of indicative of one of the biggest issues in growing that technology and accommodating those loads is the heating there, because a failure at the leading edge is a mission critical failure that can cause the airplane to lose control or actually just explode, and has definitely happened for the vehicle in the top right specifically has experienced that issue. So to address those and accommodate those thermal and aerodynamic loads, we have to do some materials science. And so we can see this graph that shows the use temperature of some of these materials, as well as the Mach number for their hypersonic vehicles. So as the use temperature goes up, well, as the Mach number goes up, the use temperature goes up. We can see like Space Shuttle Orbiter there in the middle, and old version of X-15 on the left side using Inconel. And this has to do with the speeds. The Mach number is a speed, right? So Mach 1 is 1 time the speed of sound, and Mach 10 would be 10 times the speed of sound. And the higher you go up in Mach number, the more heat the leading edge experiences and the more thermal loads you have to accommodate. So this problem becomes very large at high Mach numbers. And what's actually happening here is that the airplane is going so fast that it splits, well, the air molecules in the air interact with the shock wave of the hypersonic vehicle, and that's a chemical reaction that provides a lot of heat to the leading edge. And so the faster you go, the more intense that becomes. And one of the ways that they want to try and accommodate these thermal loads is by creating an internal structure in the leading edge that could run fluids through it and potentially take some of the thermal loading right at the tip where the heating is the highest, the convective heating is the highest, and move it back to other places in the wing where the heat can be radiated away. And so if you can accelerate this process, you can reduce the temperature at the leading edge, which can either let your vehicle go faster or last longer or require less maintenance. And potentially, if you were to use working fluid that is the vehicle's own fuel and such, you could potentially get an efficiency benefit from heating the vehicle's fuel through using the aerodynamic and aerothermal heating at the leading edge. And so that was the primary motivation for the research. There's many concepts for these. Some of them are shown on the screen. You can see it on the left side, just like the most basic version of the leading edge. It's just completely filled in. I think that's a carbon composite there. And then the two on the right side are these concepts for liquid cooled leading edges. But these are using traditional milling methods or traditional manufacturing methods. And you can already see that there's some stresses there in the center right at the leading edge where there's some kinking going on. And on the right side, you can see that the geometry is rather straight, and you can pretty much tell this was milled out. And for such a complex problem, these simple geometries may not be sufficient to accommodate the thermal loading at the leading edge. So my research aimed to combine this problem with high temperature metal additive manufacturing. So over at Center for Electromechanics, we have this lens machine, and that can print metals and polymers, as well as high temperature ceramics. And as we can see, the manufacturing capabilities of additive manufacturing it opens up many doors for different geometries. So you're no longer restricted to these simple shapes that or processes with these heat pipes that we were before. We can sort of create any geometry. It's like including lattice structures like on the right side. And if we combine this kind of geometric freedom and try to use that to address the aerothermal heating problem on leading edges, well, we could potentially come up with a more effective geometry that wouldn't be able to be made before, but with today's technology, could enable cheaper hypersonic vehicles, reusable hypersonic vehicles, especially for ones that use air-breathing engines. So not orbital reentry vehicles, but just atmosphere-to-atmosphere vehicles or space planes. And so we can just see an aerothermal analysis here. As you can see at the leading edge, at the high Mach number, the temperature is the highest. If we can put our new geometry there, we can accommodate these loads and reduce the overall temperature well, we can reduce the highest temperature on the vehicle. these are some concepts for the liquid cooling leading edges, and you can't see a lot of images of these things. You can only see really concepts because producing these kinds of geometries is so difficult. Even the ones shown are you can produce them with traditional methods, but you just haven't seen them on a production scale used on an aircraft because of how inaccessible their manufacturing methods are. So these both run fluids through the wing to remove some of the heat coming in from the leading edge and move it to other parts of the vehicle. So my research this summer was combining that science with additive manufacturing techniques to create a model for a next generation hypersonic vehicle leading edge that has these cooling channels in it. So the same way as the image before, we'd get some heat here at the leading edge and might be taken back to these channels. This part here was printed on an SLA machine at UT Austin that as a fluid would come in through the center and go in through the front and facilitate heat transfer away from the leading edge to other parts of the vehicle, like back here, where it can be radiated away. And this should reduce the temperature of the leading edge significantly enough that lower temperature materials could be used. Things like high temperature metals as opposed to ceramics or carbon composites, which, like Brian was saying earlier, there's a big motivation to do that considering the advantages of using metals on these vehicles. So here's some more pictures of that leading edge geometry. And just a concept of what this could look like in the metal. There's a lot of different places. There's a bunch of different angles you can take this problem at. We looked at material science and the aerothermal and aerodynamic conditions. Like Brian was talking about, there are so many different ways to approach this problem. It's very interesting to research and to learn about. And so getting on this project was very interesting and a lot of fun. And just learning about how those decisions are made by engineers was very fascinating and something I think I want to continue working on. So I'm very happy to present my research today for National Manufacturing Day. You have to consider all these material properties and such as well. So it's sort of this huge problem. It's like the more you look into it, there's more variables and things like the 3D printer itself changes material properties of the metal. And so you have to account for all of that as you're doing your design and qualifying the part for production. So that was my research over this summer on additive manufacturing on liquid cooled hypersonic vehicle leading edges. At this point, I'd like to ask for any questions, if any.
I just want to add a comments based on what Brandon just presented. Brandon did a great job this summer as a summer intern students working with Dr. Beeman and me. And I'm pretty sure we're gonna organize tours either in October or November. At UTRGV, we have 2 metal machines. Brandon mentioned in his presentation, right? Those we have machines that can handle high temperature metal materials. So hopefully, you know, when you come on campus, you're gonna get a you know, kind of a taste of what this kind of additive manufacturing processes look like, the principle of these processes, and you know, especially for metal printing, it's a challenge in terms of you know, technical integration, maintenance, everything is different from like the 3D printer you have at your school, at your home. So those machines are, you're talking about $1 million machine, and because of the technology involved. But anyway, you guys ask question. I just want to add some comments here.
Is that an Inconel powder bed type printing that you're using?
Yes, this was, we analyzed both, well, we analyzed like lens technology and powder bed technology. So yeah, it was both kinds that we were analyzing. And there are some advantages and disadvantages to both. One of the things I thought was interesting was how difficult it is to extract the powder from the lattice structures on those parts. And so it made using the other process potentially advantageous for that reason.
Yeah, would you have to do any type of sintering or high temperature sintering after the powder bed to set it or anything like that?
After the first, yes, you did. And cleaning out the part and setting it up, it's like we had this eye towards the production. And when part of the report was talking about how the post-processing of the material and the logistics involved with processing the material on the part were going to be difficult. If anything, it's like for probably the main challenge is qualifying the part. But even after that, the logistics in producing a larger part with such complex geometry, it'd be difficult. But since we don't aim to have this be like a large production run, we didn't, we didn't actually think about that so much.
Okay. How much of a knockdown do you think you might be able to get on that leading edge in temperature? Is it enough to like reduce the IR signature off that leading edge?
Well, I don't remember the number off the top of my head, but there was a picture in here of a convectively cooled leading edge, this one on the right side from this NASA technical report. And that one did list, I remember that one listing the temperature difference that they achieved with this convectively cooled leading edge. And I don't remember exactly what the number would be, and I would want to tell you the number. That way you can, because I'm not sure what the IR signature on that would be, but it's significant enough that, well, it's significant enough that lower temperature materials could be used. So if you're in the situation like we were saying earlier, where you might have to switch from a carbon composite to a metal material, the benefit of cooling the leading edge with convectively cooled liquid or some other like this passive cooled pelleted heat pipe leading edge could be significant enough that you can use lower temperature materials, which I imagine that's enough to lower the IR signature somewhat, but I don't know if that's like just the lower is better, or if there's a certain threshold where being below that is advantageous.
Okay.
All right, very good. I guess if there's no more question, then we can move on to the next student presentation session. I guess from now you have to host the meeting, and Anna has to go attend another events.
Yeah, okay. So next student is Leslie. Please go ahead, Leslie.
So hi everybody, my name is Leslie de la Llama, and I've been working with the iDream4D consortium this summer, and I'm very excited to be here today to share a little bit about what I've been working on and some of the projects that we got to participate in. So today I'm going to be presenting on bioprinting using the lift process, basically preparation and printing of bioinks for biomaterial applications. This was a very exciting project to work on, and I know that it sounds a little bit overwhelming at first, but I'm going to try and break this down as best as possible. So this is a little bit about our labs. I wanted to go ahead and share kind of what our labs look like, some of the areas in which I have worked in. So this is our laser printing lab at the Texas Manufacturing Assistance Center at UTRGV. You can see the laser printer that we worked on, the preparation of the slides for printing, and then just a little close-up of our workspace. So on the right side picture, you can see our laser printer once again, and then on the left side, you can see a preparation of one of the actual slides up close. So what is LIFT? LIFT stands for laser induced forward transfer, and that is a laser printing technique that prints small droplets of any desired material. In this case, I've been working with collagen type 1 and graphene inks, but there are a multitude of different materials that you can use for this process. It's important to note that this is a layered process. So this includes a donor layer, a gap layer, and an acceptor layer. And I'll be able to explain a little bit about that on this next slide. So this is a lift theoretical diagram, which basically shows you what the lift printing process looks like in action. As you can see, that laser beam up at the top, that laser beam has been refracted through several mirrors before reaching a focusing lens. Once it hits that focusing lens, it'll go ahead and concentrate onto the donor substrate. The donor substrate is that yellow slide that you guys saw like a few slides ago. That's what that looks like. So that laser will go ahead and focus on the liquid film of material ink, and it will create kind of like an air gap. And that air gap will go ahead and expand into a bubble. And once that bubble has enough air in it, it will go ahead and deposit onto a receiver substrate. This is also called an acceptor slide. And that little gap in between the donor substrate and the receiver substrate is very essential so that the droplets can have enough space to deposit properly. And that way we can get the most desired droplet size or formation for whatever printing application we need. So some of the applications of lift, as I've mentioned, I've been working with biomaterials. So there are plenty of opportunities in the biomaterials section. I've also been able to work with sensors and electronics. So that's basically different printing patterns of conductive materials that can be used for sensor applications or for microelectronics, wearable electronics, or flexible electronics. And there, like I said, definitely a lot of applications. So this is not a limited process at all. These are just some of the areas that I've had the privilege of working in. This is about my research topic here. So this summer, I was able to go ahead and create a research question, and that was I wanted to find out the effects of process parameters on droplet formation of graphene and collagen inks for biomaterial applications. So what that means is I wanted to go ahead and see which programming, which kind of adjustments that I needed to make to the laser printing process, or how I needed to program the laser, which pulse energies needed to be used to ensure the most accurate droplet formation for the applications that we were searching for. So basically, I wanted to investigate the relationship between the printing parameters of the laser printer and the end droplet formation, and then see in what areas I could better use these results for bioprinting. So this is a little bit about the project contributions. I know that engineering is most definitely a team effort, but these are some of the areas that I was able to work in when I was doing my research. So I was able to prepare the microscope slides, as you can see at the top. That yellow tape is called Captain tape, and that is necessary for the preparation of the slides. As you can see, I've coated the slide with that material ink. And that is also very essential. I need to check a specific width. I needed to check a specific concentration of material to be sure that we could get the most accurate printing. So that's what that kind of looks like. And I'll be able to explain a little bit more step by step in one of the next slides. So that was a manual coding of the slides. And then we also got to print various samples of collagen type 1. And as you could see at the video at the bottom, we observed some of these results under a microscope so that we could see the droplet formation, the droplet size, the widths, the diameters, and then we measured that using a specific computer software because these droplets are so tiny, they definitely need a microscope to be able to be seen properly. So we worked on that this summer as well. And this is what I meant by material preparation. So as you can see, the first two pictures up at the top are the donor substrate, the donor slides. So that kind of shows the preparation of the plates with the ink formulation and the ink film at the top of the donor substrate. And then slides C can show the receiver substrate or the acceptor slide. And picture D kind of shows that the donor slide has to sit on top of the acceptor slide so that that laser can hit it just right to print the desired pattern that we want. And then, as I had mentioned, we had to measure some of the diameters, the widths, the distance between the droplets, which is also the gap. And you can see some of the images that I was able to see under the microscope as well. So we can see some more desired droplets and then some not so great printing results, but there's a lot of variation within the process. And that's why we had to test these over and over again to ensure the most accurate print for our parameters. And then also this was a research-based project, so definitely had to read a lot of articles, definitely had to do a lot of independent research as well as team research. So these are some of the articles that were important to our research. So I don't have any more slides, but I wanted to go ahead and open up for any questions. Anyone wanted to add anything?
For Leslie's work, we actually have a few graduate students working on this project as well. And this machine, this setup, we're gonna have a tour in the end, this around after 12 o'clock. And we do have, some other projects supported by this machine. I think we have a bunch of graduate and undergraduate student working on this setup and for different applications. And, lift is just part of the projects we're working on. This machine can also do laser grinding, for example, laser material removal. So lots of capabilities. So maybe in the future, when you come to our campus, we can also, show you this piece of equipment. Dr. Shenshen?
Yes. So thank you, Leslie, and thank you, Brandon, for the student section.